Hello and welcome. In this video, we're going to take a look at a technique of differentiation called implicit differentiation. Now, as a heads up, it's going to be imperative that we know how to use the chain rule and how to use our differentiation operator, such as d by dx, that notation that just simply means take the derivative of this expression with respect to this independent variable. And we're going to be looking at now moving away from explicit functions that we've been talking about so far to implicit functions. Now, you may not be familiar with that term, so let's start off with what is the difference between an explicit function and an implicit function. So we have basically been just dealing with explicit functions so far. An explicit function is where we have y being represented directly as a function of x, like y equals f of x, y equals sine x, y equals e to the x squared plus 5. It's pretty easy. You just plug a value for x in, you calculate y, and you only get one unique y for any value of x you plug in. And that's why when we graph these functions, they pass the vertical line test. But we can also really just think about any generic curve in the xy plane as still being some sort of relationship between x and y. But if it doesn't pass the vertical line test, well, then it wouldn't be an explicit function. It wouldn't pass the vertical line test. So there's more than one y value for each x. Might be a little bit more difficult to calculate y. We call these implicit functions. And maybe it's more accurate to call them curves because it's not actually a function. It's just a relationship. We could still maybe say that y depends on x, and we can plug a value of x in and calculate a corresponding y coordinate. There might be more than one, though. We can still find points using a table of values, but it ends up forming some sort of curve. We can have loops, we can have circles, all kinds of interesting shapes. So why don't we take a look at an example? All right, here I've got a curve, x squared minus xy plus y squared equals 13. And, well, let's see, there might be more than one point on this curve where x equals 4. It doesn't have to necessarily pass the vertical line test. And so you can see right here that because we have a function involving y and y squared, if we want to try to actually solve this equation for y, we make it more than one solution, because it's a quadratic in y. And it also means that we can't easily just rewrite this as y equals a function of x because of the fact that a quadratic in y can have more than one solution. And we can't have y equal more than one function of x at the same time. It can't be expressed as an explicit function. So, well, let's just take a look here. When x equals 4, of course, we can plug that in here and we can maybe find a couple coordinates. Plugging x equals 4, and then we'll just collect some like terms here. And if we write this in the form of a quadratic with y squared, y, and a constant, then hopefully we can factor. And because of that, we have two solutions, y equals 1 and y equals 3. And that gives us our 2 points, 4, 1, and 4, 3. Now, if we were to continue this, we could try different values for x. And knowing that it's a quadratic, depending on the value of x, we may find no solution for y, we may find two solutions for y, or we may find a single solution for y. So if you were to continue this, or if you want to grab software and you wanted to plot this using some software, you should find out that this is actually going to give us the shape of an ellipse centered at the origin but rotated. So we can take a look at that graph here. And here's what that graph looks like when plotted in Maple. You can see the point 4, 1 and the point 4, 3 directly above each other. So it doesn't pass the vertical line test because of those 2 points. And you can see there are many other places where, of course, it doesn't pass the vertical line test. But what we could still be doing, that might be of some interest here, is, well, each of these points would still have a tangent line, right? We could see at these 2 points that they actually have different slopes. It may make some amount of sense to take any point on this curve and we could find out how fast it's increasing or decreasing. We need a way to be able to take an implicit curve and see how we take the derivative of it. Well, that's where we use the differentiation operator. we can actually use the differentiation operator on both sides of the equation. So long as we remember that we're still treating y as being dependent on x. And when we treat y as this implicit function of x, then we have to use the chain rule. So we have to be a little bit careful with that. Let's see how we can find the slopes of the tangents at these 2 points, and then maybe we can also get the equation of the 2 lines. All right, well, given that curve and the 2 points, let's see if we can find the equations of the tangent lines. Well, first of all, we have the points already. We're really just missing slope. And once we've got slope, point slope form will allow us to put those pieces of information together and get the equation of the line. So we need to find a way to get slope out of this. And the first step in doing the derivative of this curve is to take the derivative of both sides, apply the differentiation operator to the left-hand side and right-hand side of the equation. All right, so we've got our differentiating operator. The differentiation operator in this case we're using is d by dx because we have a function in terms of x's and y, and we tend to treat y as being a function of x. So we want to find out how y is changing with respect to x. And that's our common concept of rise over run, dy by dx. So the differentiating operator, d by dx on both sides. Now, on the right-hand side, we just have a constant, and we can apply the constant rule. The constant function rule says that the derivative of 13 is just 0. But on the left-hand side, we'll have to apply the sum and difference rules, and then we'll start applying some power rules. But here's where things get a little bit tricky. Whenever we're reaching y, well, y is some implied function of x. And anytime that we are differentiating a function of x to a power, well, then we need the power rule and chain rule. So, for instance, if we were to be looking at the derivative of a function f of x all squared, our chain rule would say that this is really just 2 times that function of x to the power 1 multiplied by the derivative of the function. And so, this is the little chain rule. Well, that's really what's happening here. Y is some implied implicit function of x, and because we have that being squared, we have to use a chain rule. We'll be a little careful when we get to that stage here. Applying the sum and difference rules on the left and the constant function rule on the right. And then we have our basic power rule. And then we have our product rule. And then we have to be a little bit careful here when we reach the power rule on y. Remembering that y is really a function of x, just stated implicitly, then we'll have to use the power rule, 2y, and don't forget our chain rule. Now, it's at this stage that when we're taking the derivative of y, which we are treating as an implicit function of x, that we cannot state the derivative of y explicitly with respect to x. Instead, we use Leibniz notation here. D by dx applied to y is simply the derivative dy by dx. Whereas, of course, our independent variable, the derivative of x with respect to x, is simply just equal to 1. So this means that we're going to get an expression that involves x's, y's, and dy by dx's on the left-hand side here. And what we have at this point in time is called a differential equation. It's an equation that involves our dependent variable y as well as its derivatives. And it's actually this derivative, dy by dx, that we need that is going to give us the slope of the 2 tangent lines. So we can rearrange this differential equation. It's just an equation like any other. We can still be adding and subtracting any value from both sides of the equation. We can still multiply both sides of the equation by any non-zero value. All of those sort of standard equation properties apply. And all we really need to do is just start collecting some terms and factoring and simplifying so we can get dy by dx isolated. And once we have all of our terms that don't involve dy by dx on the right-hand side, we'll factor. And here you can kind of see I'm trying to arrange things so I have positive terms in front. And then, of course, just to get dy by dx by itself, we just need to divide both sides by the coefficient in front of the dy by dx. And because an oval has kind of some nice symmetry, you actually see that this expression for dy by dx has some interesting symmetry as well. Y minus 2x over 2y minus x. All right, now there's already something kind of weird about this. And that's the fact that, well, the derivative actually involves x's and y's. And maybe this shouldn't be too surprising. See, we started off with a function where x's and y's were just kind of a jumbled up mess in an equation. In order to find a point, we have to plug in an x, but we can find multiple y's. Well, now, because we have that kind of scenario, you need to know the x and y coordinates of a point on the curve and plug both the x and y coordinates into this derivative expression so that you can get the slope at the specific point you're looking for. So don't be too surprised. You're going to have some expression for dy by dx that needs the x and y coordinate of the point. So now we can plug those in, and then we can find out the slopes of the two tangent lines and then use point slope form in order to get the equation of the lines. So at the point 4, 1, we need to plug in all of the x's as being 4 and all of the y's as being 1, and then we can compute the slope. And we'll see at this particular point we have a positive slope, but let's check out the point 4, 3. Well, here we see we actually end up with a negative slope. And that should hopefully make sense if we look back at the picture. You can see that if we are using a ruler here, we have a negative slope at 4, 3, and the tangent would have a positive slope at 4, 1. That does make some sense. Now, using point slope form, we can use the points 4, 1 and 4, 3 as well as the two slopes. But of course, we could take these two equations and solve them explicitly for y, since every linear function can be expressed in the form of y equals mx plus b. Now, it's always a great idea to see if you've got these equations correct. And a great way to do that is to be able to take the equation of the curve as well as the equations of the line and see if you can graph them all. And if they appear to be tangent, then you're probably pretty confident you've got the correct equation. And here's what the graph of that curve and the two tangent line looks like. And you can see at the 2 points there, we definitely seem to have a proper tangent line at 4, 1 and at 4, 3. Now note that, of course, this isn't quite to scale anymore. This is trying to fit those lines on nicely. And there we have it. That is implicit differentiation. It is a matter of taking the derivative of both sides of the equation. In really, it's the chain rule. Anytime that you see that you're taking the derivative of the dependent variable, you're treating it like it's an implicit function of this independent variable. So you apply the chain rule. You can't state the derivative explicitly. So when you're taking the derivative of y with respect to x, for instance, we just have to write dy by dx. And you can solve for that using some algebra after you get the resulting differential equation. Now, of course, you could use shorthand notation. If you don't like dy by dx, you could just write y prime. But you're not going to see this f prime of x like you would maybe expect, because it's not necessarily just y equals f of x. So a little bit trickier, a little more algebra. It's definitely good for some practice. But now, of course, this kind of opens up the gateway. This will allow us to look at inverse trigonometric functions and logarithmic functions, which are just inverse functions of functions we already know how to take the derivative of. If we just rearrange the equation a little bit, we can then start taking a look at the derivative of those inverse functions. But we'll save that for our next video. Thanks for watching. I'll see you again in the next video.